Hello, my name is Michelle, and this is a continuation from the last video where we had programmed an I2C EEPROM via a microcontroller, and now our goal is to be able to program the same I2C EEPROM via an FPGA. Now, the last time we had programmed the I2C chip, we had made sure that the data that was stored in the chip looked like this. We basically read the data through first 300 bits, and this is the data that's stored in it right now, modified by Michelle and Neil, just for a little bit of fun. Neil and I worked on this project on the microcontroller together, and so I gave him a little bit of credit here for that. So, with that said, basically the first thing that we got to pay attention to is that well, let's go back out here again. Is that the order of message that has to be sent over the I2C bus to the EEPROM in order to write a piece of data, in this case one character. And we're going to send over the character A, which is a hexadecimal 41. So basically it says that we have to do the start condition, and then it talks about how that we need to do the device address, which is 10100, and then the base address, which we assigned it to just being 2 zeros. So 101000. The write bit, because we're going to write, has to be a 0. So that's the first byte, is 10100000. Then it wants the first word of the address, the first 8 bits, the most significant bits of the address. So in this case, we're going to write to the first bit of the first address, the address 1, not the first address is address 0. We're going to write to address 1, and so of 16 bits, these 8 bits would be 0. Then we would get acknowledgement from our slave, and then we would write in 00001 so that our address is at address 1, get an acknowledgement, and then we'll send over the data, which in this case I said was 41, which would be what, 0100 and then 0001. And then we would get our acknowledgement, and then we would send over the stop bit scenario, stop condition. So let's go look at what should be on this. We have to, when we do our coding, we have to make sure that we meet those start and stop conditions. So what is the start condition? Well, on the serial bus, you have 2 wires. One is the serial clock and one's for serial data. So the start condition is when both the serial clock and the serial data are in a high position. And while the clock is still in the high position, we want to literally go from a high to a low state. And so if we go look at our master code, and I go and look at my initial state here, I'm starting off with my clock and my data in a high state, and then when I get a valid piece of information, the data is going from a high to a low state. So therefore we've met our start condition, and we will go into sending over our address, serial slave clock address bit. So we go back to the thing here. So that's our start condition. And then then we would send over our data. Like I said, there was 4 pieces of data that go over there: the slave address, the high of your address that you're writing to, the low part of the address you're writing to, and then the actual data. So those 4 bytes, and each one of those 4 bytes, you send over the data you need, and then you get an acknowledgement. So whenever the system serial clock is high, you get your acknowledgement from your slave. So if you go look in my master code, the first thing I want to show you is that, so here's my slave address. Another thing that was important in this thing is to make sure that we sent the data over when we were in a low state of our clock. So basically I'm sending over my data at this point when the clock is in the low state. So therefore, and then of course when we are now in the high state, in this case we're just basically counting, we're waiting for 8 bits of data to be sent over. Once the whole 8 bits of data are sent over, then we're going to wait for our acknowledgement. In this case, I had to put the data in a high state that lets the tri-state buffer know to put the data in what's called a high impedance state, and therefore allows the actual slave device to send data back over the same wire. So we did this. We're doing this on the low clock. So now on the high clock, here we are. We're basically waiting for the data. We're checking to see if the input data we get is a 0, because that's what was required in the spec. If we go back to our spec, it's a 0 on the data coming in from the clock. So I mean from the slave. So it's a 0 thing. So that's what we're checking for. We're looking for that 0. So if the data is 0, then okay, that means we got an acknowledgement. Let's keep going. So in this case, here we are. We're sending over the high address bits, and then we get our acknowledgement. Then we're sending over our low address bits, and then we get our acknowledgement. And then we're sending over our data bits. And then here's our data acknowledgement. Once we have that, now we have to check for our stop bit, right? So we have to send over the stop bit scenario. So we go back over here and we look. Stop bit scenario is when the clock is in a high condition, you have to go from a low to a high. So we go and we look at our code, and I can see that we're in a high clock. High clock. Let me double check to see I'm saying it right. We're in a high clock going from a low to a high. Okay. So we go to our code. We'll see that we are in a high clock, and our previous state was a low data, and our next state, maintaining a high clock, we go to a high data. So our low to high during a high clock, and that is the stop state. And so therefore, my code meets the standard that's spelled out in the EEPROM specification in order to be able to work. The only other thing I want to point out to you in the code, I'm going to minimize this now, is that in my top, I had, this EEPROMs run at 400 kilohertz, right? And so basically I had to convert my 125 megahertz clock down to 400 kilohertz. And so I did a little bit of counter divider to create a generic clock that actually goes out and does that. But the other thing that's important is that like I said, I had to set up my tri-state buffer to communicate over the I2C serial bus. And so, like I said, when the output data is at a high condition, make my serial data a high impedance, therefore allowing whatever input comes in from the slave to show up on the bus. Otherwise, we'll just send over our 0. Now, it's important that the 0, we don't have it in reverse scenario, because the I2C serial bus is a open drain system, and therefore when we need to make sure that that both sides, the master and the slave, that they are the pull-up resistance on these buses allow for high impedance scenarios, but they have to make sure that they're wired to ground in between. And so therefore, that's why that 0 is very important, so that it goes to ground. And we would know that if we go into the actual I'll get to that in a minute. I'll show you the schematic. But if you look in the schematic, you'll see that that is ground. Oh, well, so this is the sim of what I had done. And you'd be able to see, if I pull up I'll pull up my test bench here. You can see here's my main clock. Here's my actual clock. And then you can, and so I'm just sending over my data from my test bench. Basically, I'm getting the 1010000001 during, if you'll look, so that's just saying that oh no, these are all zeros. My bad. 10100000. Now, whenever I'm in the high SDA, remember the told you had to be in the high, it goes to high impedance. I need to get a low clock data. And so while this is high and this is my actual clock, I'm getting a low data. So that's where my acknowledgement actually is happening right here. Um, then, of course, I sent over the high portion of the bits of my address, which would be all zeros. And then again, here I go to 1. I'm high impedance. I'm at a high clock, and I'm getting a 0 from there. So that's acknowledgement. Then the next one is so that's the low portion of my data address bit, which is 1. So here's my all my zeros, and there's my 1. And then, of course, I'm getting high here for high impedance. I'm in the high clock, and there's my 0 that I got from my slave. And then, of course, the next one is 41, which was the data I'm sending over, which is 01000001. And then here's my high, going back to high, with my clock being high, which is a high impedance environment. And here's my 0 acknowledgement. And of course, if you looked at my states, you can't really see them here, but all my states are here, and you can see that I go to my state here, my stop state. Here's my stop. Here's my stop low, stop high, and then my stop. And there's my transition from. It's going from a low to high state during a high clock. If you look down here, we were in a high clock with a high to low state. There's our start state, which you can see my states, my state here is start. That's my, actually the previous state, you can't really see it. It's so built into here, but there's my idle. And then here's the beginning of where I'm actually sending over my address, my slave address. So it sims out like it's supposed to. My data is being sent over. Like I said, I was sending over 00001, and then 41 was my data I'm sending over. Okay, so I'm going to close that out, my sim. Like I said, I'll go ahead and show you in my schematic the, yeah, we don't want to open design. We don't want to rerun the synthesis. In order to be able to not use a processor to send over data, I had to hard code the data in that we're sending over. All right, so here we go. Here is my SDA bus, and here is where it's actually going to ground. That's the important piece right here. This is my input from my master. Let me zoom out a little bit so you can kind of see that. Here's my input from my master. And then this actually is what the input from the slave. It'll come in here, and if you open this up, it'll kind of show you how it's all put together, how it comes in and goes out this buffer. And it goes as my input to my master. So that way, we're actually, my output, my master is going out the SDA, and then when the slave is returning information, it literally is being funneled back into my master. And that's what the schematic looks like. All right, so we'll close that out. And so, like I said, as I said before, the data that's sitting in there right now is the modified by Michelle and Neil. So we're going to send over the first address. This is address 0, this is address 1. So I'm going to send over character A. So if we did it right, when we go to read the EEPROM again, it should say modified by Michelle. Okay. So like I said, I had to take a picture of that because I'm not connected to the EEPROM anymore. I'm connected to my FPGA. All right. So now what we're going to do is we're going to go ahead and turn on my FPGA, so it's running. Everything's connected. I'm going to go ahead and open my hardware manager because it's already, bitstream's already created. We'll open my target and auto connect it. All right, waiting for it to connect to my FPGA. And then basically what we're going to do is program it. Once it's all connected, there it goes. Then I'm going to program the FPGA. Now, I also created an ILA so we could see what's going on in the FPGA itself. So I'm going to go ahead, and this is, so we're literally running an ILA right now. And so here's my, like I said, my input buffer, here's my tri-state, here's my output buffer, and then here's my valid. So it's, when I say it's valid, literally it will start sending data. And so that's, so we're going to, so we basically said trigger on when valid, when it's going from 0 to 1, which is basically R means 0 to 1 transition. So when I'm literally saying I got a valid data, I want to trigger on it and catch it. All right, so right now I'm going to say let's start running. So we're waiting for trigger, it's idle. I'm going to turn off my reset on my FPGA, so now it's live. I'm now going to say valid and not valid. So it's valid. Boop, there it goes. And so the FPGA said, okay, well, let's go see what you did when you're valid. Now I'm going to hit this thing onto reset because we're not going to do anything anymore. All right, so well, let's go take a look and see what happened here. Let's we'll zoom in a little bit maybe. Do we need to zoom in? Yeah, we need to zoom in a little bit here. Once there. And then let's move this over so we can take a look at what the FPGA did. Just like our, it was just like our uh, sim. We basically did a 1, 0, 1, 0, 0, 0. Here was our high impedance, and here's our 0 data for acknowledgement. So we got our acknowledgement from our slave. Here's our address 0 for the high bits of our address. It went high impedance, and then we got our 0 data input buffer. Here's our 0001, and then we went high impedance again. Oh, right, here's our high impedance, and then here's our 0. All right, so that's address 01, and then our data, which was 01, 00001, and then here we're in high again at this clock, and there's our answer, our low impedance. And if I zoomed in more, you'd be able to see where we go from our low to high, while this is we got a high clock, and therefore we're in the stop condition. So literally, if I zoom in one more time, we might be able to see a better look at that maybe. Yeah. And so let me see if I got here. This is 001, and then address. Yeah, right in here. This where I'm gonna move this over so I can see it. Right. Where is our there's our acknowledgement. So yeah, so basically their stop condition is somewhere in here. So here's the message that got sent over to this FPGA. All right. So let's go ahead and turn off my FPGA. We'll pull my I2C EEPROM off of the FPGA. And right now, while I know you can't see what I'm doing it in the background. I'm going to go ahead and pull up my code that I'm reading. So I'm going to wire up my FPGA real quick. Let me get my glasses on so I can see what I'm doing. So right now I'm literally wiring up the power, and now I'm wiring up the ground from my microcontroller to my EEPROM. Now I'm wiring up my clock and data bus to the pins. And hold on, there we go. There they are. So we're all plugged in. I'm going to take my serial port, my USB port, plug it into my microcontroller. So now that's live and powered is on. I'm actually going to go ahead and open up my serial monitor, and then I'm going to run it. And so it's going to compile here, and we're going to wait here and see what happens. Right now it's compiling. And then we're going to, now it's basically going to send a program the microcontroller with the program that basically just reads the first 300 bits. And now it's running, and whoa, looky there. It's modified. Sure enough, we changed that first bit from modified to modified. And so it successfully changed the bit on the FPGA, and we're reading it right now from. Now, my next section that I'm going to have to work on is being able to read, obviously, from the EEPROM via FPGA, that code. And then I also need to work on being able to literally send over and read from the microcontroller that's built into the FPGA. So I don't have to keep plugging it into my ESP32 microcontroller. So those are the next steps into this design, but I thought I'd report in the progress that we're making. And so I hope you enjoyed this video. But there you go. We've actually programmed this EEPROM, I2C EEPROM via my FPGA. Thank you and have a good day.